Hello everybody, and welcome back to another geometry lesson. Today we're going to take a look at 7.5, which is all about trapezoids and kites. You may recall that we started this sheet last time. Last time we started an organizer to help us talk about all the different types of quadrilaterals. Today we are continuing that chart to talk about trapezoids and kites. So what's a trapezoid? Well, a trapezoid only has one restriction, one thing which says that it must be a trapezoid. That is that it has exactly one pair of parallel sides. As long as it has just one pair and not two, it is going to be a trapezoid. Now, this is not very restrictive. That could mean that a lot of shapes are trapezoids. This could be a trapezoid, maybe a malformed parallelogram, where one side is actually longer than the other one. As long as these two are parallel, it's a trapezoid. Trapezoids could be anything. So we also have to specify that there is a type of trapezoid that is the same on both sides. An isosceles trapezoid is a trapezoid where the two sides, here and here, called the legs, are congruent. So for an isosceles trapezoid, one pair of them, or one pair of sides, has to be congruent. We call those the legs. One pair of congruent legs. Another thing about isosceles trapezoids is diagonals across them also appear like this to be congruent. It's because they are. They don't cut each other in half like parallelograms do, otherwise they'd be possibly a type of parallelogram. They do, however, have congruent diagonals. Diagonals are congruent. Finally, we take a look at the angles at the very bottom of an isosceles trapezoid. We see that these two angles look like they should be the same. But also, we can look at the very top of the isosceles trapezoid and see that those two angles are the same. Folks, when we talked about isosceles triangles, we had a base and the base angles. Trapezoids have two bases, so they have two pairs of base angles. Two pairs of congruent base angles. Very nice. Kites are quite possibly the strangest of them all. We have so many different properties that kites have just based on their funky shape. For those who don't know, a kite is what happens when you have two pairs of congruent sides that, instead of being across from each other, are next to each other. We say that we have two pairs of congruent consecutive sides. So the sides that are congruent must be next to each other, not opposite each other. Another thing that we notice about kites is this. When we take a look at a kite, and we split it up into diagonals. In fact, let me draw a little bit of a bigger kite here on the back side. There we go, let's give us enough space. If we were to draw a big kite like this, let's say I've got it this way, and then let's do this and this. If we draw out the diagonals of this kite, something immediately happens when we draw the first one. Because we have these two sides that are congruent, and these two sides that are congruent, and we know that the middle side is congruent to itself, by side-side-side triangle congruence, these two halves are congruent triangles. So we can write that down as well. We can say that it can be viewed as a pair of triangles sharing a side. A pair of congruent triangles, more specifically. Let's take a look at the second diagonal. Once we draw the second diagonal, a lot of things become very clear. The top part of the kite, with these two sides, is an isosceles triangle since the sides are the same, so we know the base angles will be the same. Similarly, this is an isosceles triangle, so these base angles are going to have to be the same. Essentially, when you have a kite like this, we can split it into two isosceles triangles. The shorter diagonal splits it into two isosceles triangles. What else? What we see here that these two diagonals also make right angles, so they are perpendicular. We can say that the diagonals are perpendicular. And last but most certainly not least, well, actually we have two more properties, I apologize. But with the diagonals at least, the last thing that's important here is that this big diagonal is cutting the small one in half. So these diagonals are congruent. One of the diagonals is bisected by the other. One diagonal is bisected by the other. Last but most certainly not least, if we look at the angles here and here, in between the two non-congruent sides, we see that those two angles are the same. So it has one pair of congruent opposite angles. That is the weirdness of the kite. So we are now going to take a look at some definitions, fill them in, and get some practice. Let's start off with the trapezoids. First of all, a trapezoid is a quadrilateral with exactly one pair of parallel sides. As long as it's got one, it's a trapezoid. The base angles are the two angles that were on the bottom and the top of an isosceles trapezoid. If your trapezoid's isosceles, these base angles are going to be congruent. So we say we say the base angles are the angles that lie on the same base and when we talk about isosceles trapezoids, we see that these two angles will be congruent. So the isosceles trapezoid base angles theorem says if a trapezoid is isosceles, then its base angles are congruent. We've got two different pairs of base angles. They don't all need to be congruent to each other, but the pairs of base angles are congruent. An isosceles trapezoid, however, is specifically when we have those two legs on either side of the trapezoid that are congruent. So if you see a trapezoid where the legs are congruent, it's an isosceles trapezoid. So once again, the definition is a trapezoid with a pair of congruent legs. Cool. Next up we have the isosceles trapezoid base angles converse. The isosceles trapezoid base angles converse is sort of the opposite of this. This says if you know something's isosceles, then the base angles are congruent. This one says if a trapezoid's base angles are congruent, then it is isosceles. Cool. Next up, when we talk about an isosceles trapezoid, we can see that the diagonals across the trapezoid are congruent to each other. They're the same length. So, if a trapezoid is isosceles, then the diagonals are congruent. Fantastic. The last trapezoid definition I want to talk about is going to be the trapezoid mid-segment theorem. And this is a weird one. We've dealt with mid-segments before when we were talking about triangles. But we never did it while talking about trapezoids. So first off, what is a mid-segment? As a reminder, a mid-segment is the line segment that connects the two opposite legs of a shape. In this case, the mid-segment is going to cut through the two non-parallel sides, but it will also be parallel to the parallel sides. Because it cuts it in half, we know that these two will be the same, and these two will be the same. But there is something else that we can figure out. Believe it or not, we can actually figure out how long this mid-segment is if we know the lengths of the other two bases. So for instance, let's say this top base is 10 inches long, and the bottom base is 20 inches long. Since the mid-segment is exactly in the middle, it's actually going to be halfway between 10 and 20 inches. It's going to be 15 inches. So, the trapezoid mid-segment theorem says the following. The mid-segment of a trapezoid is parallel to each base and is half the sum of the base lengths. So if you can add together the two bases and divide by 2, you'll get the length of the mid-segment. The formula for this looks like 1/2 base 1 plus base 2 equals your mid-segment. Since we're already almost to the end here, I want to mention a couple more definitions. One of them, however, is missing, so I'd like to add one down below here. A kite. We need to talk about what defines a kite. A kite is defined as a quadrilateral with two pairs of consecutive congruent sides. But the opposite sides are not congruent. So a kite is a quadrilateral that has two pairs of consecutive congruent sides. It means the sides that are right next to each other must be the same length. This and this, this and this. I'll just erase this here. We do have a diagonal theorem for the kites as well. We say that diagonals of a kite must be perpendicular. If a quadrilateral is a kite, then the diagonals are perpendicular, just like in a rhombus. The kite opposite angles theorem says that there is exactly one pair of congruent opposite angles. So, if a quadrilateral is a kite, then it has exactly one pair of congruent opposite angles. There we go. Alright, folks, let's take a look at the next page, the last page of Unit 7. We'll take a look at some examples here. So, this one says to show that ORST is a trapezoid, and then figure out if it's isosceles. Well, in order for something to be a trapezoid, there has to be exactly one pair of parallel sides, right? We know that, just from looking at it, the pair of parallel sides is going to be RS and OT. But it's not enough just to show that those two sides are parallel. We need to also show that RO and ST are not parallel. 4 slopes, folks. We need to find 4 slopes here. So, let's find the slope from R to S, the slope from S to T, the slope from T to O, and the slope from O to R. To go from R to S, I go up 1, right 2, so it's slope of 1/2. To go from S to T, I go down 2, right 2, it's negative 2 over 2, which we know simplifies down to negative 1. TO, I have to go down 2, left 4, so it's negative 2 over negative 4, which simplifies to 1/2. We've got our match here, so we know that these two are parallel. Now we need to show that OR is not the same slope as this one. And since to go from O to R, it's just up 3 over 0, we call that type of slope undefined. So since negative 1 and undefined are two different slopes, we say ORST is a trapezoid. Cool. But how do we figure out if it's an isosceles trapezoid? Well, in an isosceles trapezoid, the two legs, the ones that are not parallel, have to be congruent. So, let's see if this is congruent to this. We can find the distances of these two sides and compare them. Let's do it. So we know that to find the distance of both of these, we'll have to use the distance formula. Or do we have to? You see, the distance from O to R is just a vertical line. It doesn't go left or right at all, so it's just going to be 3. We can count the squares since it's straight up and down. For S and T, though, we will have to use the distance formula. So, we can subtract the two x values, square it, subtract the two y values, square it, and we get the square root of 8 when all is said and done. If these two are not the same, we can say not isosceles. If these distances were the same, it would be. Cool. For example 2, we have to find the length of the midsegment. The midsegment is YZ, right? Because that's the only length that's bisecting both legs. But to find the length of that segment is a bit tricky because Z isn't a perfect point. Y is, Z is not. So we might need some extra help to do this. Luckily, we have that trapezoid midsegment theorem. The trapezoid midsegment theorem says that the midsegment is equal to 1/2 the sum of the bases. In other words, YZ is going to equal 1/2 of SV plus TU. All we have to do is find the lengths of these two bases, add them together, and cut them in half. So let's do it. To find the distance for SV, we'll use the distance formula once again. Subtract the two y values, subtract the two x values. The distance from S to V looks like it's going to be the square root of 20. For those who are curious about what the square root of 20 is as a decimal, we end up getting the square root of 20 is 4.47. We can do the same thing for TU. TU, all we have to do is do y2 minus y1 squared, x2 minus x1 squared. For this one, it's a little bit bigger. We get the square root of 80, which, if you were curious, the square root of 80 is going to be 8.94. So to find YZ, we should just add these two together and divide by 2. When we do that, when we add 4.47 plus 8.94, we get 13.41. When we divide it by 2, we get that the length of YZ is going to be 6.71, approximately. Cool. Again, all you have to do is find the lengths of the two bases, add them up, and divide by 2. Let's move on. In example 3, we have to find the measure of each angle in the isosceles trapezoids and kites. Because we know that these are isosceles trapezoids, we know that they are going to have congruent base angle pairs. So L and M are going to be congruent, and K and J are going to be congruent, so we should figure out the rest. Since K and J are congruent, that means J is going to have a measure of 118 degrees, because the same as K. It's the base angles that are congruent. But finding L and M is a bit tougher. Instead, here is a hint. Since these two angles are the same, we can say that they're both x, an unknown. Since all quadrilaterals add up to 360 in terms of their degrees, we know that 118 plus 118 plus x should be 360. When we add together all four angles, we get 360. This means that 236, oops, sorry, my pen is dying on me. Let's try an exactly similar pen. 236 plus 2x equals 360. So when we subtract 236 from both sides, we get that 2x is going to equal 124. So when we divide by 2, x has to be 62 degrees. We have now found all four angles. 118, 118, 62, 62. There is, however, a shorter process to this. Let's take a look at these two numbers, 118 and 62. Is there anything that we notice about those numbers? Well, if we add 118 plus 62, don't we get 180 degrees? It turns out that the consecutive angles that are not base pairs add up to 180. They're supplementary. So in part B, for instance, even though we know that these two angles will have to be the same, so R is 82 degrees, to find the other angles, to find the missing parts, we can just subtract 180. 180 minus 82 is going to give us 98, so both T and Q are 98 degrees. Done. And if you check, you'll see that it adds up to 360. Very nice. Next up, I'm going to show you part C, and then I'm going to have you try out the rest of these problems on your own. We're dealing with kites now, folks, and with kites, there's only one fact about the angles that we really know. That is that there is exactly one pair of congruent opposite angles. Once again, we don't know what either of these are, but we know they're congruent, so let's set them equal to x. We can then say that all the angles have to add up to 360 and solve. We'll get 140 plus 2x equals 360, which means that 2x equals 220. Both of these angles, E and G, are 110 degrees. I'd like you to pause the video here and try out problems D, E, and F. Come back and unpause when you are all set with those three. How'd you do? I tried to trick you a little bit with E and F. Recall that they have one pair of opposite congruent angles. It means that F and H here are congruent. These two wouldn't be x's. These two would be. You wouldn't set up the equation in the same way. If you did want to set up an equation for this, what you really would be saying is 110 plus 110 plus 60 equals 360, and then find out the remaining angle is 80. So, for the next two examples, that down here, example 4, we have this picture of a cake, and we know the following facts. NP, this top layer of the cake, has a diameter of 8 inches. LR, this third layer of the cake, has a diameter of 20 inches. And we have to find the diameter of the bottom layer of the cake. This isn't going to be so easy because, unfortunately, none of these little mid-segments are mid-segments of the entire trapezoid. But we can figure out some information here. For instance, let's ignore the bottom of the cake for right now. We do have an isosceles trapezoid. The legs are congruent. And we know the top and the bottom. So can't we find out the middle? The mid-segment here is half of the two bases added together. Since 20 plus 8 is 28, half of that gives us 14 inches. So we can figure out the second tier of the cake. But what do we do about the bottom? Well, here's the interesting bit. We now know that the mid-segment of this bottom trapezoid is 20. One of the bases is 14. We used to figure out what base 2 is. We can solve for it using this formula. The midsegment of a trapezoid is 1/2 base 1 plus base 2, and we know most of this information. We know that 20 has to equal 1/2 of 14 plus base 2. So we can undo this equation. To get rid of 1/2, I'm going to multiply both sides by 2 to get 40 equals 14 plus base 2. And when we subtract 14 from both sides, we find that base 2 should be 26 inches long. Here we go. Last, most certainly not least, we have a proof. Now, this is a bit of a longer proof, but it demonstrates something really important. Sometimes, when you are given the diagonals of a shape, you should focus less on their lengths. Apologies. Sometimes you focus less on their lengths and more on the fact that you've got some triangles that are created. We always start each proof by giving our given. So QRST is an isosceles trapezoid. That is our given. But from here we get a bit stuck. You see, just because it's an isosceles trapezoid, we don't know that these angles are going to be the same. We are actually trying to prove that angle TQS, that's this angle I'm going to mark in blue, is congruent to SRT, which I'm going to mark in red. So we need to figure out how to do that. Anytime you're given a definition, you should always use that definition. An isosceles trapezoid's definition is that the two legs are congruent, so we can say that QT is congruent to RS because of the definition of an isosceles trapezoid. Nice. Right away we might notice something a little bit interesting. You see, when we have a side that's congruent in both of these shapes, we might start to think of them as triangles. Notice that with these sides, we can actually make two triangles. Triangle TQS and triangle SRT. Well, now, right away we can pick out the fact that TS and ST are actually the same line. That's just the reflexive property that says that. By the reflexive property, we know that this side's the same. If we wanted to prove these two triangles are congruent, which I kind of do actually, we just need either one side here or one angle here. While there are multiple ways of doing this proof, I'm going to use the isosceles trapezoid diagonals theorem. If you recall, that's the one that says this. If a trapezoid's isosceles, the diagonals are congruent. So QS must be congruent to RT. We now have two triangles. I'm going to shade in a little bit just so we can see which ones we're talking about. Two triangles, a blue one and a red one, that have three sides that are congruent to each other. This means the two triangles are congruent by side, side, side. So first off, this one was the isosceles trapezoid diagonals theorem. But by side, 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 we know that triangle TQS is congruent to triangle SRT. If Finally, this comes together with the following. If you know that two triangles are congruent, then you know each part of the triangles are congruent. The thing that says that if these two triangles are congruent, then the angles up here are congruent, is corresponding parts of congruent triangles are congruent. CPCTC. And that is the ending proof of Unit 7. Thank you so much, everybody. Have a fantastic rest of your day, and I'll catch you next time.